Hi everybody, great to be here in Paris again to talk about Apache Kafka. So before I start the talk, I wonder who knows Apache Kafka, who is using it? Is that okay? Around, I would say, yeah, 70–80%, that's cool. And the goal of this talk is really a little bit to connect the dots between two very different topics. Machine learning on the one side, where data scientists build analytic models, and then Apache Kafka, where we really bring things to production at scale. And this combination is a huge challenge at many of our customers, and I really want today to connect the dots and show you how that can work and can look like. And I will also show a short live demo at the end that you get a better feeling of that. Instead of doing just a technical introduction, it's more about telling your story today. This is in the end what we see at our customers, how they do that, and that's what I want to show today. In this example, what I'm doing, I'm using the example of an automotive company who has built a connected car infrastructure, and based on that, they want to leverage and build more business value by using machine learning. So the main idea really is, in this case, the connected car infrastructure is already there. That's just where also many of our customers are already, like Audi, for example, as automotive example. They today, like in this example, are already there, that they have a connected car infrastructure. So they connect to thousands and in the future millions of cars which send data in real time to a Kafka cluster, and then you can correlate the data and also send data back to the cars. And what I want to talk about today is how you can leverage machine learning to add even more value to these kind of infrastructures. Therefore, my point is really, when we talk about machine learning, and actually on Monday I was at another machine learning conference where people talk a lot about deep learning and image recognition, speech translation, or then of course autonomous cars. That's all great stories, and a lot of this is already valuable today. But what we see even more important today is really how to improve existing business processes, because that's also what you can do with machine learning. So you can do fancy new stuff or the normal stuff and improve that. Here are a few examples like fraud detection, which exists for 20–30 years in payment, right? And with machine learning, you can improve that. Or on the other side, something like predictive maintenance. That's the example which I will show today, how you can use machine learning to improve the detection of anomalies, to detect before a car engine breaks, for example. So there's many use cases where you can leverage machine learning. And while I don't want to spend too much time on defining what it is and so on, it's really just one picture here to explain that machine learning in my talk here means that you want to find hidden insights without being explicitly programmed where to look. So taking a look at a lot of data and analyze it, aggregate it, and then get insights from that to do predictions on future data. So therefore, machine learning, that's a lot of different algorithms you can use. Here's just a few examples of most common ones, like decision trees or clustering. And then, of course, also there's this kind of deep learning buzzword, which is in the end neural networks, which you can use. And there are then several subtopics like convolutional neural networks for image detection, for example. In my example, at the end, I will use an autoencoder, which is doing anomaly detection to detect anomalies in the car engine and the sensors. But the point is really, it doesn't matter which kind of algorithms you use. Pick the best one for your use case or for your problem. What I talk about today with Kafka is really true for all of them, and it works together with all of them. Just pick the right one for your business problem and use it. Therefore, in this story now, if we think about how do you build analytic models, and that's really what we see at so many of our customers. So you have a data scientist who typically uses Python and then some machine learning framework. In this example here, TensorFlow or maybe anything else, doesn't matter much here. So you create a great model, and that does great predictions for your use case. And that's also how these kind of tutorials work. When you go to a TensorFlow website or any other machine learning framework, you see how to write 20 lines of Python code to do great predictions with a great model. The big problem, however, is creating a model is one thing on historical data, but how to bring that to production, meaning think about the connected car infrastructure. If you have millions of cars sending data in real time all the time, how do you set this up reliably? Both training the model with all the data ingested, but then also applying the model to do predictions and monitoring all of that. 24/7 without downtime, without data loss. That's really critical, and that's much harder than just building a model with some Python code. And to show this even more, here's a great picture from a white paper from Google where they explained about the hidden technical debt in machine learning systems. And here you see what it really takes to bring machine learning into production in a mission-critical, scalable infrastructure. So it's much more than this small thing in the middle. In the back, you probably can't even read it. So this is ML code, the black box. This is the Python code you write to train a model. So this is a small part of what you have to do. And most data scientists also don't spend most of their time with that, what is the fun part, but they spend most of their time with data analysis, data preparation. And then together with the engineers or production team to do all of that at scale. For example, things like data collection. That works like in the tutorials when you read from a CSV file or even from a Hadoop system from a big data set. But if you have to ingest from millions of cars, that's another kind of technology challenge which you have to solve. And then the same story for things like data verification or serving the infrastructure for doing the predictions. And then, of course, another part which many don't think about when they build model, you have to monitor all of that in real time, both from a technical infrastructure perspective and then also from the business perspective, how that works. And therefore, it's a huge challenge to bring machine learning into production at scale. However, the good news is many companies have already solved this problem because they had exactly these challenges before. The white paper was from Google. I also have a few other examples. Like Netflix, for example, has built a very powerful recommendation engine which analyzes all the data which you give them in real time to send you back the right recommendation for you. So for every user, the right context, the right information at the right time. So everybody of you, when you use your iPad or computer, you get different recommendations from Netflix. Another example is Uber. They have built a ML framework, Michelangelo, and that's really a big framework which supports many frameworks under the hood. It's not just about one ML framework like TensorFlow. You have to be able to use different ones for your specific business problems. And then do the whole process of data science from ingesting the data, pre-processing, training, monitoring, deploying at scale. And that's what Uber is talking a lot about, their framework. And the third example is PayPal. They have a lot of use cases for fraud detection and have implemented many different analytic models to find the different kind of malicious code or other intrusions, how they do wrong payments or something like this. So and the main point, and this is also now to connect the dots again. The one side is the problem and to train models. And then in these examples and many others, you will find out when you take a look at their blog posts and talks and architecture, that they use Apache Kafka heavily in these kind of architectures. And the reason for that is to build scalable and reliable infrastructures where you can also do this kind of data science process. Therefore, most of you know Apache Kafka already. If you don't know it, here's just one slide to describe it. We always call it an event streaming platform. And the most important part, I think, is that you need to understand, and maybe not sure if everybody knows it, but Kafka is not just a messaging system. So Kafka is much more than that. So as you see here on the right side, yes, it's PubSub, so you produce events, and then they are stored in Kafka, and then some other consumers consume the events. And so it's publish, subscribe messaging, but that's only one part of Kafka. The second part is as important. It's also a storage system, a scalable distributed commit log. And with that, you can store data as long as you want in Kafka. And with that, you have huge advantages. You decouple the different producers and consumers from each other. So for example, one consumer could be a real-time fraud detection system, and another one could be a batch analytics system, like Hadoop or Spark, or maybe something like Elasticsearch, where you do near real-time indexing the data. And so this is a very important combination of messaging and storage. And then as third part, you can also process the data natively with Kafka. That's what I will show later also in the demo a little bit. It's just an option, of course, but you don't have to send all the data to a Spark cluster or so to process it. You can do it, but you can also do it natively with Kafka. And there's always trade-offs. There's sometimes this is better, sometimes that is better. But please be aware simply that Kafka is not just a messaging system, it's messaging and storage and processing data, what you can do with that. And with that in mind, probably most of you know Kafka was created at LinkedIn over 10 years ago, and then it was adopted by many other tech companies. So here is just a few examples, but you can really try it out afterwards. Just Google for any tech company from Silicon Valley and Kafka, and you will probably find something what they do with Kafka. And so here are just two examples. So today, LinkedIn processes over 4.5 trillion messages per day with Kafka. Or Netflix processes over 6 petabyte data per day with Kafka. And that's not the movies, right? They are in a content delivery network. That's just the messages they send. That's 6 petabytes of data for Netflix today. And important here also to understand is that Kafka is not just used by tech companies. So today, every bigger company on the planet has several Kafka projects because it's used for so many different use cases. And the second one, which is even more important to understand, Kafka is not just used for big data. Yes, that's important, and that's what it was built for. But today, I would say that maybe 70–80% of use cases are not about big data. It's more about processing maybe gigabytes per day or terabytes. But it's really, many use cases are just about important critical transactions like payments or fraud. That's not petabytes of data per day. So this is where it's coming from. And Kafka is used a lot, that's what I said. So here's just a few examples of use cases, because this kind of streaming platform with messaging and storage and processing in one platform, you can do many things much easier and better than with other systems which tried to do that in the past. And therefore, I don't want to go into too much detail here. The main message for our customers typically is focus really on a use case which adds some kind of business value, whatever that is, like increase revenue, reduce cost, mitigate risk, and then build your project around that. It doesn't help if you just build a data lake to store all your data if you don't get any value out of that. And therefore, I've just listed some examples of what customers are doing. And it's really getting more and more important in infrastructures. And it's really getting the core central nervous system in many deployments. And that means really that every event which is happening is running via Kafka. And that's true for many tech companies like LinkedIn, Netflix, eBay, or whatever. But that's in the meantime even true for many traditional companies. So we see, for example, more and more banks which build their core banking system around Kafka in the meantime. And with that, they still integrate to the mainframe because they cannot replace it within a few years. It's not that easy. But the central nervous system is the event-based and scalable Kafka infrastructure. And then you can build use cases around it, like Customer 360 for real-time analysis of your customer, or you can do big data processing like IoT sensor ingestion and processing. That's the use case of today, more or less. And of course, then you can also do things like cybersecurity much easier, or fraud detection. So there's plenty of use cases for Kafka. This is just to give you a little bit overview. And so now, again, let's move back to machine learning in Kafka, the main topic of today, to connect the dots again. How does this work together? Because we have seen before that it's a huge challenge. Think about the use case connected car infrastructure, how to integrate and process all the big data sets for that. And if you think about machine learning is two parts. It's always training a model on historical data, and then you have a model, and then you deploy it somewhere to use it for predictions on future events, right? To get a probability of what if something is happening or not. And so this is in the end what you see here. So you see a lot of different sources which create data. This might be mobile apps or mainframes or whatever it is, and they create data. And this is used somewhere to train a model. That's the first step. And then the second step is that you deploy your model in a production app where you use it to do predictions in the future. And this is the main architecture. And here, as you see, Kafka is really a perfect fit, and that's why so many use it. You can, with Kafka Connect, or even with just clients like Java or .NET or Python, you can integrate with many different systems. And on the other side, you can also then deploy your models within Kafka applications easily. So that's also important to understand. Kafka is not just the broker in the middle, which is the messaging and storage part of Kafka, but it's a whole open source ecosystem which you can use to do other things. That's all optional, but you can use Kafka Connect to integrate with a database or a messaging system or Elasticsearch or Hadoop. There you get a lot of out-of-the-box functionality regarding throughput, availability, reliability, and so on. Just to give a few examples. So this is the main idea, how you can make everybody happy, both the data scientists, because they can build their model on the historical data with their favorite machine learning framework. But on the other side, also build a reliable and scalable infrastructure, both for model training and also for model deployment. And then, of course, also for monitoring all of that. So with that in mind, with this architecture, let's come back to our connected car infrastructure. So as I said, in this example, the company already has the infrastructure for that. They have built that already in the last 2 or 3 years. Therefore, this is in the end the setup. In this case, we have the devices, which are the cars, and they are sent to the Kafka cluster in the cloud. In this case, we are some kind of MQTT proxy. This is just one example of how you integrate such a technology. In this case, they use MQTT standards. That was built not with the idea of machine learning in the beginning. It was just to integrate all the data in real time in a scalable way to process it. And the motivation in this example of automotive companies, they are doing that to build new use cases, because automotive companies cannot just build cars in the future anymore. They have to add additional digital services. Otherwise, they will be out of business or not as important as before. And I'm based in Germany. I see it with all the automotive companies. So if they don't do it today, then Apple and maybe Google will come there and make most of the money with the digital services. So this is the main infrastructure. We now have, in this example, have it in a Kafka cluster on Amazon Cloud. And that's running 24/7 and scalable and everything works. But now we want to also train model to even improve some of these use cases. So therefore, we can use our ingested data, which is coming there in real time at scale. However, in this case, the big problem is, and that's really not just for this example here, but what we see in the real world a lot, that in this example now, the analytics team works on Google Cloud. So they are working in a different infrastructure. And it's a very common scenario which we see. Either that's, for example, the main integration is on-premise, and then an analytics team works on another cloud provider. Or in the meantime, we see more and more people which use multi-cloud for many different reasons. Different features, different cost, compliance reason, logistics, whatever. So in this case, we use a replication tool to replicate all the data in real time from the ingestion cluster to the analytics cluster. And this, by the way, is exactly what Audi is doing, for example. So they have the ingestion cluster, which is the most critical one. This one has to run 24/7 without data loss. Because if this is down, everything behind that is also not working anymore well. So this is the one which is the most critical one, and from this you replicate to an analytics cluster, for example, and maybe to other clusters for other use cases. The analytics cluster might not be that critical, because if that's down for 2 hours, that might be okay, because you just train models. And you also can train the models 2 hours later in most use cases. So now we have it on Google Cloud, and now we can focus on our machine learning process. So here, one big part, of course, is pre-processing the data. Pre-processing often means things which are not related directly to machine learning, like filtering or transformations or aggregations or anonymizations. If you get millions of sensor events per event or other custom information from the drivers, then you have to do that at the same scale. You process millions of events, and therefore Kafka is perfect for that. And you have the Kafka pipeline anyway. So why not use also the Kafka native technologies to process the data in real time in a continuous streaming way? So you can do that either with Kafka Streams, which is a part of the Apache Kafka project. That's also what many people don't know when they talk about Kafka. Kafka is the message broker, which is messaging and storage, right? But it's also Kafka Connect for integration and Kafka Streams for processing. That's all included in the Apache Kafka project. And in addition to that, you could also use KSQL, which is a community project from Confluent, which you can find on GitHub. That is the same story. It's also natively using Kafka with all the advantages it has: high scalability, high throughput, reliability, and so on. However, you just have to write SQL queries to do that. And in contrary to Java, which is Kafka Streams, which is good if you know and want to write Java, here you just write SQL codes. And therefore, this is, of course, a perfect combination for a different audience, like data scientists, which are used to use SQL or Python. And here you can do rapid prototyping with KSQL. For example, on GitHub, I have an example where I do it in a Jupyter notebook with Python and KSQL. So that's familiar for the data scientist. But it also connects the dots to deploying it later. Because the data scientist can develop this query in his Python notebook, but then the same query can be deployed to production. You can deploy this query to KSQL servers and scale it up and down and process millions of events per second. Because this query under the hood is using Kafka Streams, and that is using Kafka under the hood. So that's pretty powerful, but it's also very easy to use. So there's no coding around. You just deploy this script without any kind of code and scale it to millions of messages per second. So that's a pretty cool thing for pre-processing in the machine learning step. As next step then, so we have ingested all the data and processed it. So now we are close to training our model. For that, we typically have to store it in a data store, like in Google Cloud Storage or in S3 or whatever. So here again, we can use Kafka Connect. Kafka Connect is part of Kafka, and it allows you to integrate with different sources and things by leveraging all the features of Kafka: high throughput, high scale, high availability, and all these things. And also, you can also integrate with different systems. And in the big projects we see, people don't use just one storage or one machine learning framework. They use different ones for many different reasons. So sometimes a different team wants to use something for a different problem. And for example, for deep learning, you probably use TensorFlow or something like this. But maybe for some random forest processing, you use a different framework, which is better for that. And so in the end, that's the way how you ingest the data into some kind of data store to train the models. And then finally, we are there to train the model after all these kind of steps before. This is now the part where the data scientist writes the Python code, 20, 50, 100 lines of code, to define the model with the hyperparameters and train one or more models to evaluate them. This is, by the way, why we see so many analytics teams working in the cloud. This is the best thing in the cloud, because here you can use extreme scale to train your model, maybe for a few days, maybe even with GPUs or TensorFlow processing units in Google, so TPUs, which are specifically built for deep learning. With that, you can do training at extreme scale, maybe for 3 days, and then you shut it down again. You just pay for it when you use it. So that's perfect for training models. And so after this process then, this, by the way, of course, that's not related at all to Kafka. So you ingest it with Kafka and process it, and then you store it somewhere and train the model. Then you get a model out of that, which you can then use again. So that's the normal flow we see today. You store it in S3, in HDFS, whatever, to train your model. What's now even cooler is that in the meantime, there is even possibility to ingest the data directly from Kafka into frameworks like TensorFlow. This means you have some kind of streaming machine learning where you stream the data from a Kafka topic directly into the TensorFlow engine. And with that, the big advantage is you don't need another data store. Right? So that's pretty easy for many use cases. It's a much simpler architecture because you save one component. You don't need an HDFS anymore. You just ingest, in this case, sensor data into TensorFlow to train the model. This, again, has probably its trade-offs, right? So sometimes you still want Spark or HDFS or S3 to store it. But it's an option, and in many use cases, you simply make your architecture much easier and your workflow much easier to do. Another reason why we see more and more Kafka also related to machine learning is that Kafka is a commit log. That means you append the data here, and then it's stored here in an immutable way. This means that you can train different models the same way. Same order is guaranteed, then you have timestamps, and you can consume the data again and again in the same order. And that's exactly what you want to do when you want to train different models and compare them against each other. So, and that's pretty easy with Kafka. You just consume it. Let's say you say, consume and get me all data from the last 7 or 30 days, consume it and train my model with that. And then you could either train 2 different models with one framework, like with TensorFlow, and compare them against each other. And then you deploy the one which works best. And then maybe half a year later, there comes a new tool. Like in this case, something like AutoML with DataRobot. And then you say, well, our TensorFlow models are okay, but let's try out something different. And then even if it's a year later, as long as you have still stored the data in Kafka, you just connect another consumer, which uses DataRobot, and consume the same data again, and you can still compare the models to each other. So that's pretty cool with Kafka to train models with that. So now we are in the state, okay, we have trained our model, right? This is in the end the story. We have a model, and a model is just a binary in the end. Depending on the framework, this can be protobuf, like with TensorFlow, this can be Java code, this can be some proprietary stuff. Doesn't matter, it's a binary which you want to deploy somewhere to do predictions. So this is totally now not related to the training process, and that's a good thing. Because now, in this use case, like for the connected car infrastructure, we have sent all the data to the cloud, we have anonymized it and used it to train models. That's okay in the cloud. However, in this use case, for example, it's not allowed to process the real customer data in real time to do predictions in the cloud, because often this is compliance issues or other reasons, or maybe it's performance because it's long latency then. And therefore, you can, for example, deploy this model now in an application on-premise, which communicates with a local Kafka cluster. For example, for Audi, what they're doing, they're deploying different Kafka clusters, like in Germany or then in Switzerland or whatever, and in the future also in the US and Asia. And there you can do then local processing and predictions by applying the model. So this is totally separated, and that's, I think, a good thing typically. And now we have to think about how do you deploy a model and do the predictions. So what's the normal behavior of what most people know today is that you build your client application which does the predictions. And for that, it uses then a model server where the model is deployed. That's what many people do today. So like in this case with TensorFlow serving, where you deploy your model in a TensorFlow server, or maybe also with other tools, like for SAS, for example. That's all the same story. They have a server where you deploy your models. And then some applications do an RPC call to send the data there, and then do the prediction here, and send the model, the prediction back to the client application. This is good and okay, and sometimes it's good enough. Sometimes even, for example, for TensorFlow, at least you use gRPC, which is a pretty good RPC communication tool with good performance. Most other technologies use HTTP here, which is already harder to do and to scale and to do reliable. But no matter which technology you use for RPC, you always have to do a remote procedure call to somewhere else. And the main two challenges are first, of course, scalability. Think about connected car infrastructure, millions of events which have to do RPC calls here all the time. And the second part, which is even harder to do then, what do you do in case of failure? If this network is down, or if there are some other problems here, you have to implement a lot of complex error handling around that. And therefore, while for some use cases, this is a totally fine solution here with a model server, another option is that you simply directly embed your analytic model into the client application. And in case of Kafka, it's a real-time streaming application. And if you use Kafka Streams or KSQL, you can easily embed your model there. Why is that possible? Because a model is just some binary which you embed there. So this can either be done in a manual process, or this can be done with some continuous integration. Or in the meantime, we even see more and more customers which train the model in the back end in the cloud somewhere, depending on the use case, every week, every day, every hour. And when the training is finished and the model is good, then they send it to a Kafka topic which is consumed from the application, so that you can do it without complex migration processes and use new models in application. But the huge benefit is now that you don't have the problem that you have to do remote procedure calls for doing the predictions. They're running here inside the real-time application. And that makes it more performant, better scalable, more reliable, and you don't have to care about a lot of error handling. It's all a trade-off. Sometimes this one is the better one, right? There's always trade-offs, but you just should be aware this is an option which often is a great use case, especially if you need model predictions at scale in a reliable way. So now we talked about model training and model deployment. The last part, of course, is also which you have to think about from the beginning and not after you have built your infrastructure. How do you monitor all that? Both from an infrastructure perspective, is both the model training and the model predictions and all the infrastructure for that, is that working? Do we lose messages? Do we get duplicates? What's the latency end-to-end? That's another very important thing. When you produce data, for example, from a car, send it to the cloud, and then also want to send information back to the car, for example, an alert that the engine is breaking, then you need to know the latency between all that. So it's important from a technical infrastructure perspective and also from a business perspective, both for the business use case regarding improving automotive processes and also regarding machine learning and the models. How accurate are my models? Are they working well? Should we really retrain it every week, or do we need to do it every day? And therefore, if you have a Kafka infrastructure anyway, I think then it's obvious, of course, most of our customers then also use Kafka to build this kind of monitoring around that. Because it's the same scale, it's the same real time, it's the same advantages. And you don't need another technology in addition. So this is in the end how I want to show you today to connect these kind of dots between machine learning and data scientist and production deployments. And so now I also want to show you a short example so that you get a better feeling of how that looks like. So here is our connected car infrastructure. And on the left side, we see the car sensors which create data. And in this case, we use the MQTT proxy to get the data into a Kafka cluster. This is a pretty nice architecture, and that's, again, mostly what we heard from many automotive and manufacturing companies. They use MQTT a lot in the meantime. However, the main reason is also that the devices support it, and also that they can get into Kafka easily. But actually, they don't want to use an MQTT broker in the middle, because in the end, the main reason is to send it to Kafka to integrate with all their other backend applications. And therefore, one option is an MQTT proxy with that. That's part more or less of the Kafka cluster. In this way, you can even integrate with MQTT clients without using an MQTT broker in the middle, because that's then, again, additional cost and complexity for deployment and so on. All with the trade-offs, again, like always. But for many use cases like this, it's a much easier architecture to use. And then you have it in Kafka, and then in this case, we use a KSQL application where we apply our model. So this is where our model is deployed in a real-time scalable application where we do predictions and send it back to Kafka. And then from here, we can send this information to the rest of the world. With consumers, different consumers can consume the data. In this example here, you have Elasticsearch, which is more near real-time, which indexes the data into their search engine. And on the other side, this is for all the data, for every prediction. And on the other side, we have a emergency system which only consumes the potential defects, so only a small part of the data, but the critical one where you really have to send an alert to the driver so that he stops his car very soon. And what I want to show you today is not the whole system, so that's a little bit too much for such a talk, but I have most of this implemented on my GitHub examples. What I want to show you is the part of the deployment here. In this case, we have the KSQL application. And as you see here, this is a very simple query. We create a stream based on a Kafka topic, and then select, in this case, the sensor ID of the car, and use a user-defined function which has the sensor values for each single event. And based on that, we use the prediction that's implemented here under the hood. You write a user-defined function once, like you do it for an Oracle database or any other system, and then every end user can use it without knowing the details about how it's implemented. And in this case, it does real-time predictions on the sensor data at scale. So let's take a short look at that. So the only thing I have already done, I have already started my Kafka ecosystem. So I have used the Confluent command line interface here. That's pretty easy for development. With one command, you can start everything. And so more or less, we are ready on my laptop to do what I just explained. I'm here on my GitHub page, so as you see, I have a few different Kafka and machine learning examples, not just for TensorFlow, but also for H2O and deep learning for J, for example. And so we will take now a look at one of these examples. That's exactly what you have seen on the slide. And with this, I will go relatively quickly through this, and not in full detail, but just that you get a feeling about what's going on. And so the first thing I do is I create a Kafka topic. A Kafka topic is where producers send the data to, like the cars, and where others consume it from them. Like in this case, the KSQL application, which does the predictions in real time. So here you see the topic is temperature, so that simulates my car engine sensor. And with that now, we have just to do one more thing to start, and that's the MQTT proxy. The MQTT proxy is now, it's also another part of the Confluent components for Kafka, which is in the end now a proxy, which is started here. And this is waiting for MQTT devices to create messages. So I have no MQTT broker running here. It's really just this proxy based on the Kafka technologies. And this is waiting now for messages. And then, as next step, what I do, in this case, I start my KSQL interface. So this is a command line interface which you can use for development. So similar, like if you do it from the Python or Jupyter notebook, right? Here I do it in the terminal. And here now you can do things like list tables or whatever you want to do. This is just to do some commands. And with this now, we can use KSQL to create queries. And in this example, we create one query car sensor. It's a pretty simple one, and in the real world, of course, it's a little bit more complex. But here we consume from our temperature, and in this case, the value format is delimited, so it's simple CSV data from the sensor. Of course, you can also use other things here like JSON or Afro, for example. And the point is now I created the stream, and with this stream now running, I can create queries on that. And in this example, again, I do a very trivial query here. So I just say, select event ID and use my anomaly function, which is a UDF, to get the sensor input from the car sensor. And the anomaly function under the hood uses the analytic model to do the real-time prediction. So now just what we need to do is to create data. So what I'm doing here, as you see, I use MosquitoPub. MosquitoPub is a client for MQTT. So this in the end simulates the MQTT interface, right, in a real world example. So it's a client side. It's not an MQTT broker. It's really just a client like from a car, for example. And here you see the sensor data. This is now one message. And as soon as I will press the return button, it will send the data to the MQTT proxy, which forwards it to the KSQL query here. And from here, you will get the result in real time. So, and that's what you see here. The real time, the result is in the middle. It's just the ID, right? Then the 5 nines, and it's the prediction. The prediction in this case is a value. What this value means, that is what your business people and data scientists know, because that's how they define their model. And then in the real world, you would define, for example, a threshold that over a specific threshold, you decide that this is alert and you have to get a car engine braking or so. So here I now started a sensor generator to create some random values. And this is now just a very simple example. This is one car, one sensor, 5 nines ID. And it creates different values. And based on these values, which are sent to a Kafka topic, and from there consumed from KSQL and processed, as you see here, for every new event, it applies the machine learning model and sends output back. And that's our prediction. And we could, for example, have a threshold as soon as a car, for example, sends a value over 5 and maybe 10 of these values within 1 hour, so a sliding window or something like this, then send an alert to the driver on his mobile app or to the car directly to say, hey, stop in the next 10 kilometers or your engine will break probably. So that's in the end how this kind of example works. And the important thing is also now you can, of course, do more powerful stuff. And I won't go through this due to time constraints here, but here is a few other examples how you can filter and transform that a little bit more. And then, of course, the last important thing is, and then after KSQL has processed it, it's going to a Kafka topic. So from there, every other consumer, like Elasticsearch or any other Java application, can consume it again. And now, again, what's important to point out, these kind of KSQL queries, they are pretty easy to write, but they can be deployed in this way to production at scale for millions of events to a distributed KSQL infrastructure. And that's pretty powerful and simple at once. And finally, I just want to show you the implementation of this UDF. I don't want to go into detail here. The point is really how simple it is also to write even user-defined functions with KSQL. KSQL has the main functions out of the box, like aggregations, filtering, and all these things. But of course, if you want to use your own TensorFlow model, then you have to write this code once to apply it here. And as you see in the top, it's really just, in the end, one interface which you have to implement. That's the function for the user-defined function. And then you also simply add what you want to add. And in this case, I just import one library for my model. In this example, it's H2O. And in this case, I just embed this library. And then I can use it here. And you just get as parameter the sensor input in this case. And then you do some transformation. And then here the main code is the prediction. It's one line of code where you do the prediction here in the middle, right? And that's happening in real time. And then you're sending the information back to the Kafka topic, to the next one again. And that's it. And this is a very simple example again. You can do much more powerful and complex things here. You can also do aggregated functions with state, for example. And therefore, that's in the end what I wanted to show you. So just finally to mention, as I said, all of these examples and much more is also on GitHub if you want to take a look. So you can also try it out by yourself. And with that, what I explained to you, this is in the end really what we're doing with Confluent with our customers. We build mission-critical systems around Kafka with all the ecosystem around it. We focus on the ecosystem like monitoring, operations, security, and all these things. And that's in the end our main goal. So as you really see, we focus on Kafka a lot. So here's just an example of, this is around the last 2 years or so about the commits to Apache Kafka project, right? So, so we really heavily focus on that project and build our whole technology on that and expertise. And with that, What I've shown you today about the connected car infrastructure, that's really what most of our customers do. They build hybrid deployments because typically they don't start greenfield in one cloud. They start on-premise with their legacy applications and continue that in their data centers and combine it with applications in the cloud where you can either run Kafka self-managed by yourself or you simply use a service provider like Confluent Platform or Confluent Cloud where you get it with specific SLAs for uptime, throughput, latency, and all these things. And that's in the end what I want to show today. I hope you got a good overview about really how to connect the dots between machine learning and the Apache Kafka ecosystem and how to build systems at scale with that. Thank you.